Today we're going to do naming compounds. Technically, it's inorganic. You don't need to worry about it too much. There's another lesson on organic chemistry, which is the other type of naming. Anyway, this is the naming that everyone first learns. It's the mixture of all the elements. By a strict definition, it doesn't contain carbon-hydrogen bonds. And this first little blurb here just talks about how lots of people claimed they had compounds. And then over the years, people have come up with techniques. They could be simple like combustion or harder to pull off like electrolysis using electricity to split it. And eventually those compounds are being divided into their element constituents. And over the years, they've narrowed down all the 118 elements that, this isn't up to date, but there's 118 to this date. And eventually they realized the concept of the atom, protons, neutrons, and electrons all made up these elements, and so on and so on. But as a scientist, the first thing that you need to realize, or a chemist, I should say, first thing that you need to realize is that this periodic table is organized in the way, and it works, and kind of you never have to memorize it, you just got to know how to read it. So first thing that you need to understand is that every group, every column, they call it groups, every column, the elements in that column are very similar to each other. Okay, they're mostly similar through chemical properties. That means they react in the same ratio. They kind of behave the same. They look the same. There is some physical property trends, but it's mostly chemical properties. I'm not going to dive too deep into that, but if you could firstly just try to grasp what Niels Bohr, he kind of knew this periodic table worked and invented the idea of electron shells. So he said, the reason why everything works is because in the first shell, the first row of the periodic table, there can be 2 electrons in that group. And in the second one, where there's 8 elements, we can have 8 electrons. And in the third row, we can have 8 electrons as well, even though that's technically 18. We'll gloss over that. That's a year 11 topic. And that was really powerful. It wasn't kind of justified, but it had a really strong explanation power. So now the way to visualize the periodic table is everything in one column has the same number of outer shell electrons, and the word for outer shell is valence. So that same number of valence shells, that one electron means it always is going to react with 1 electron or lose that 1 electron. And group 2 has 2 electrons to react with. And over here in group 7, they've got 1 more electron. And the thing that you need to understand is that pretty much everything just tries to achieve a full shell. Okay, I'm going to use some examples. So for instance, diatomic elements, you would never find hydrogen by itself. It just would have 1 really reactive electron. It has an incomplete shell. So if you're ever going to find hydrogen, it'll be paired with itself, right? And through sharing, both these hydrogens have a complete shell. So through sharing, they both have 2. Because it has 2, we call it, it's more likely to be stable, it's unreactive, and this is the way we find it in nature. Similarly, you'll never find oxygen by itself. It's got 2 spots or 2 places before it completes its shell. By the way, things on the left-hand side lose their electrons, and things on the right-hand side gain electrons. Metals lose, non-metals gain. So oxygen needs to gain 2 electrons, and through sharing it does that, and does it twice. It's called a double bond. And these 2 oxygens both have 8 in their outer shells, so they have full shells. And that goes for all compounds. Water, through sharing, hydrogen has 2, through sharing, oxygen has 8, and this goes the same through all of them. Carbon's got 2 double bonds either side of it, and so each bond has 2 electrons, so 2, 2, 2, 2 makes 8. And a little subtle thing I guess you need to know is you'll see here nitrogen has a lone pair of electrons, so it's in group 5, so you would draw nitrogen as like this, 1, 2, 3, and draw it a bit better. The 2 lone pairs of electrons up here, we call them unreactive, and the 3 spots, I'm going to draw the spots as like this, makes nitrogen reactive. It can pull in 3 electrons, so to say. Right, that's background. Now into naming. First thing that you need to be able to do is look at the periodic table and go, what's a metal and what's a non-metal? Okay, and we'll get to that later. And if you recognize that it's a metal and a non-metal, you're in the ionic naming system. Okay. If you recognize it's a non-metal and a non-metal, you're in the covalent naming system. Co means sharing, valent means outer shell electrons, ionic means charge. And if it's metal and metal, or metal by itself, lucky for us, there's no naming system. It'd be like an alloy, like for instance, brass is 66% copper and 34% zinc, or stainless steel, which is a mixture of iron, chromium, and carbon. Right, so if you've recognized that it's metal and a non-metal, which is like the hidden rule, what's going to happen is a transfer of electrons from the metal to the non-metal. So you would name the metal first, and then the non-metal second. If it was sodium chloride, the most common thing, you'd name the metal first sodium, chlorine, and then you change the ending to I to represent that they're chemically bonded to each other. Okay, that it's not just sodium and chlorine sitting next to each other without any transfer. It's sodium and chlorine. There's been a transfer of electrons, and now they're attracted to each other. The only time, rule number 1A says the only time you don't do that is if you see these kind of guys. And at first you just get it as a cheat sheet, and then eventually they're memorized. But if you see these kind of what are called polyatomic, many-atomed ions, so they're nitrogen, hydrogen is two atoms, and they're an ion, which means they have a charge overall. You just kind of use their names as is. So if you see these guys, you don't change the ending to "ide," even though hydroxide already has that. So you just call it phosphate. And the other thing is, if you see a transition metal, then you need to use Roman numerals to denote the Roman numerals to denote the charge of the transition metal. So in this case, it's iron 2 chloride and Fe2 plus, and in this case, it's iron 1 chloride because iron's charge is 1. For covalent, you're going to just name the left-hand side non-metal first, right-hand side second, and then use prefixes to state how many are present. Mono, di, tri, tetra, penta, hexa, hepta, octa. 5 and beyond is just shapes, so it's not too hard. Quick thing about ionic compounds, so you understand them, is they're the transfer of electrons. So for instance, sodium would lose that 1 electron to a group 7, and then because they're opposite in charge, they'd be attracted to each other. I've done magnesium sulfur because they would react in a 1-to-1 ratio. He needs to lose 2, he needs to gain 2. And then I gave a hard example with aluminium and oxygen. Aluminium needs to lose 3, oxygen needs to gain 2. So the ratio that they need to come together to satisfy that transfer is a 2-to-3 ratio, and you get aluminium 2, oxygen 3. You can kind of think about it like a lowest common denominator.